Okay, so this is going out to the 3D graphics people. I needed to build some way of dehumidifying my filament. As you can see, I've got the P1S, I've got the A1 or the AMS, and I needed to be able to do this. I've been trying to come up with something for a long time. I've looked into people who have built risers, they've built this, they've built that, the Deskin packets, all kinds of great stuff I have purchased in the past. You know, your boss, whatever that is. Dryer, and I would dry my filament, and I would use Deskin packets in here. And as you can see, I store all of my stuff nice and neatly in their original plastic till it comes time to use it, and then I put it in the thing. It helps me keep down on the humidity. Well, this is Oregon, and it's not Seattle. It's not it's not Aberdeen. It's not out there on the coast up here. But we get really bad humidity, especially in the fall. Okay, go into the long diatribe. It's not as bad, or doesn't feel as bad in the spring because temperatures are rising. But in the fall, the temperatures are coming down, the barometer is coming down, and it feels like you're walking through a pool. I'm not kidding. I've got a full-size dehumidifier, little portable, little big ass, holds a gallon of water, portable dehumidifier, and that thing fills up within about 6 hours, and you've got to dump it. Okay, it is, the humidity here is running at about 60 to 64 during the day, depending on whether the sun is out, and whether or not it's drying up the grass and getting all that water in the air. So having a heated AMS has been something that I've been wanting to do dehumidifying. I'm going to cover a bunch of different things because there's a lot of different people who don't understand stuff. I might do like a very shorter video of the AMS or the heating system that I released. This is the long version. So sit back, relax, get ready for a long talk and discussion on how to dry filament and all the different characteristics and things you have to take into consideration. CAD and designing is new for me. I'm not new to the computer world at all. But doing actual CAD work on a computer is new. So like my first project was getting a vent system out that window that didn't block the whole window and do stuff. That was one of my first projects. But this was next. And so the CAD system that I'm using is Onshape. I'm more of a mechanical engineer. So, you know, it's mesh-based systems just are kind of nuts to me. So Blender, Tinker, SketchUp, those guys, I just know the way they do it. I explained it to somebody once, and I said, you know what? It's a different kind of brain. It's biological nature, and it's religious in conviction. Okay, you are either a mesh type or you are a parametric type, and I'm parametric. I could do 360. 360 is one of the original AutoCAD, out there guys, and they've been doing this for a long time. So they're both parametric and compatible with mesh, but it's also super highly complex, over what I need type of thing. It's kind of overkill. Onshape is really good for this because it's parametric, and it's simplified enough to where I'm not ambushed by too much stuff that I just don't need. Okay. For what I want to do. So when it comes to drying filament and dealing with reducing your humidity, Okay, three main methods of doing this. Okay, I'm sure you guys all know we've done the desiccant packets. Okay, it's kind of like sitting there and saying that there's three states of matter. There's solid, liquid, and gas. You have physical things, desiccants, that suck water, that are hygroscopic, more hygroscopic than air, and suck the water out of the air and hold the water for you. The other way of dehumidifying is to raise the temperature of the air. Okay, that's when you use a heater, and what you're doing is you're creating a deficit of humidity versus capacity. Okay, it doesn't matter that it's 64% humid in here if I'm heating the air before it goes in, and it's capable of holding 75. The air now has a deficit of 10, 15, 20% humidity, and it's more hygroscopic. It's going to do, it's kind of like low pressure versus high pressure. It's going to suck the water out of the filament. It's going to suck the water out of what's in there, take it with it out the vent holes, and then release it out here. Okay, you're trying to create something that sucks up the water, okay, and takes it out. The third method is through cooling, okay, and that's when you create a cold surface that causes the water to basically condensate, stick to the plates, drip away, and you're taking the water out of the air that way. Okay, so you you chill the water, causes it to become a liquid, and you can take it away from the air that way. You can have some physical piece that's more hygroscopic and it sucks the water out of the air. Or you make the air hotter, more capable of holding more water, so it sucks out the water and takes it with you. Basic three ways of doing it, okay? And in true fashion, I'm basically looking at using all three possibly. Right now I'm just using two. We all have the little desiccant buckets that we put into the front. There's some new ones that have the skinny ones you can put on the side. I've had to change these things. Well, not change them, but I've had to nuke wave those beads about 3 times in the last week because of how humid it is. And not only how humid it is, but because I've been constantly taking this on and off and on and off and doing testing and all this other stuff. So the first version that I came up with was this one. This was version number 1. And what I was doing is my focus was not changing the AMS system as all. I did not want to damage the hood. I didn't want to damage the body. I know you can buy a new one. It's 35 bucks for that. It's 50 bucks for this. But I don't want to spend that money on something if I can just print something, especially if I'm going to be printing about 1 billion of these anyways. You have to have some way of mounting this heating ability, this heating system, and injecting it into the side. So what I had was basically a system where I extended the size of the body, I made it taller, and I took the pre-existing hood and I put hinges, I did the whole 9 yards. You can see it fits nicely in there. Got it together, and I created a working prototype. And the prototype worked. I wanted to make sure that the heating system would work. All right, the heating system, you're going to have to craft these together. All right, you can get these thermostats for about $10 if you like centigrade. All right, let's go ahead and bring it closer. You can get these thermostats, all right, for about $10. If you don't mind centigrade, you're going to pay 15 to 20, like me, if you like dealing with Fahrenheit, because we're American and you're lucky I'm using metric, okay? Just deal with it. So I got my Fahrenheit, and then this heater. The cool thing about this heater is this heater, okay? It's a PTC heater, okay? So it's using a plate, or it's electrifying basically an aluminum coil, which is your heat sink, if you would. And then it's blowing a fan across it here and blowing in. Use your thermostat with a temperature probe that goes in over here. It's right in front of this, okay, so that it's detecting the temperature. You'll notice that it goes pretty high and then pretty low. That's because it takes time between this plate heating up, transferring heat to the air that's coming through, then having the air transfer the heat to the probe, and by the time that happens, this thing goes off at 115. I have it set to 115 because that way it'll vary, okay, between about 109 here. When it finally realizes, oh, I got to turn back on, and it turned on, and it's been cooling. Oh, now we're able to bring the temperature back up. It's this little wave of pattern. So the delay between the time when it starts cooling down and the time when that temperature change in the coil is actually read by a meter, because it's transferred from solid to gas back to another solid, allows it to get up pretty hot, and then it cools and goes up and down. So it fluctuates pretty good. The ones that you see in the EBOS, those ones are tuned so that the PTC metal stays at a certain temperature all the time. Okay, and it takes more electronics to do that, and by doing it this way, you're staying relatively inexpensive. All right, you're not throwing additional pieces in, so $10 for this and $20 for this, and you're golden. What I like about this one, I got the thermostat and the PTC that run on 110. You can get a lot of them that run on 12 volts, but then you're dealing with having to buy power supplies and so forth. This plugs straight into the unit. Now, I did take the existing one so that I could wire it. And I rewired. What I did is I took the cable that goes directly from here. It's a nice little cable that you can disconnect. I'm trying not to pop it, but it disconnects so that I can take the unit and go if I needed to, but I plug it in, and basically I cut this wire from here. I shortened the length so that so I wasn't using up too much space in here. Yes, I haven't trimmed the thermostat wire yet because it's way too long, or the thermal probe wire because it's way too long, and I didn't want to shove it all in here. Wired the power through a switch through here, running power up to this. I can show you a wire diagram if you need to, but there's a million of them out there. Okay, but you do have to cut the wire so you can put all these pieces in. If I turn it off, that's power switch for everything. Power on. The fan stays on all the time. The heater turns on and off as the thermostat goes. So it's wired to do that. All right, this was the second version. The first version, I wanted to test a lot of different things, one of which was the heat coming off this plate with that variance. What kind of damage would that high level of heat, I know people are going to say you can go up to 150, what kind of heat can this unit take? This, nice and cool now, okay? When you take a look at this system, you'll see that there's basically, okay, 1, 2, 3, 4, 5 main pieces. Actually 6, sorry. Why? Because there's a vent cover on the inside. So 6 pieces. You've got your thermostat box with power switch piece. The power switches, you get these like a dozen for $10. Unfortunately, you got to buy a 5-pack or a 6-pack or whatever of them to get it. You can buy a 40-pack for like $15. You know, they're cheap little things, but you've got to buy a bunch of them to make it worthwhile for Amazon to ship that shit. So you've got your switch in your thermostat box. You've got your heater mount. Okay, this is the heat mount system, and what it's doing is 2 pieces. One, it gives me a little bit of distance between the heat that comes in and your spools. Okay, so it's not directly hitting the spools. Number 2, it's shaped into a half circle, because if you look at the side from over here into your AMS, you'll see that you can only see half of the center. And I'm going to grab a couple of these real quick. All right. Now the other problem is that you have different size spools. I use Sunlu like crazy. It's pretty much my go-to. I'm Sunlu and PETG. Those are my go-tos. But Bambu, and I know a lot of you use it, that is the main difference between these. It's not this, okay? It's not the size of the spool this way. It's not the size of the inside spool this way for these two sizes from here to here. It's the size of the inner core, okay? And the reason for Bambu having such a small inner core is because they come apart and they have a locking system that does that. That's what they're using up that inside space for, causing the circle to be smaller. So this has been sized so that it's blowing the air very easily through Sunlu, but it still blows the air nicely through Bambu. So if you've got Bambu spools and that's what you use, you're going to be okay with this, because I've catered it to that size. In the first version, I basically just used something to blow the air down. And in the first version, you can see a little bit here that I used silicone. I wrapped silicone in here, and silicone is great. You know, they make hand mitts and oven mitts and all kinds of stuff out of silicone. Standard silicone, any silicone off the shelf is going to handle 450 degrees. Better stuff, 500, or the ones they brag about are 500. It's a whopping 50 degrees, no big deal. But the next step up typically is about 7, and the top step is usually around 9. I think they're trying to come out with some stuff that's 11, but right now most of the stuff you'll see is either 5, 7, or 9. And anything off the shelf, I don't care if it's caulking, if it's silicone in a gun for using around your windows. You buy that stuff, doesn't matter. That's 450, that's good enough. The heater I'm using is a 200 watt. Okay, this is a 200 watt. The heat on this, the max heat with the fan on, okay, is 200 and about 60 degrees, okay? That's how hot this can get. That's hotter than you want it. These are all variables that I took into consideration on the idea that, well, what happens if the thermostat goes out? What if this thing is blowing full blast, 260 degrees? I'm going to lose some filaments. I'm going to lose this, but is the damn thing going to catch fire? It's going to burn my house down. These were the big concerns, okay? First one, I didn't want to even change this, but I wanted to make sure that no matter what kind of failure happened, nothing on the house is going to burn down, okay? Well, when it comes to insulating against the heat to your plastic, your PTG, this is PETG, you can use silicone. Silicone is great, like with oven mitts, because you're only going to pick that plate up for a minute or two, and it slows down the heat transfer for a minute. That's easy. That's easy for silicone to do, and it can get to really high temperatures and do that against really high temperatures. But after a minute or two, yeah, your hands are burning. Okay, you're going to be burning. All right. Anybody who does welding and grabs a frickin' new weld with their glove, yeah, it's protecting you for about a minute, and then it's going to burn like hell, and you got to throw that glove off. Okay. Same thing you're dealing with here. So you need something that has a higher thermal barrier, and one thing that has a really great high thermal barrier is wood. Wood, paper. You've got a burn point of about 450 degrees, so you're 200 degrees higher than this. So the end solution for this was to not just put a layer of silicone inside. I used the silicone as a glue. So I put the silicone inside, and then I took basically a paper roll. You could use a toilet roll. I used one for a paper towel. I used paper towel. I cut it down. I cut it open. I actually made two pieces, and I just I put a whole bunch of stuff in there, and then I just put it on, and I let it snap on and dry. Okay, so now this side the inside has silicone and paper. I did cut a hole through the paper for where I push the thermostat in right here, and then I recoated the hole with silicone so that it would have a layer of silicone. The reason being is that when I shove the thermostat in, I kind of have to push it through. After it dried, I cut to create basically like a grommet, a rubber grommet, so that when I push the thermostat through, it would go through, close up over the wire, and then really kind of hold the wire and the probe right there, so it's not just waggling around. The reason being is because, again, the way these heaters work, even though there's a guard, it works by electrifying that metal. Don't touch the metal if you got it turned on. That's going to electrocute your butt. So that's why they put the guards on here. Now, so it's guarded, it's kept back, but it's not, wiggling around, floating, and I can keep it real close to the temperature, and I get very quick response times, or the quickest response times I've been able to get. So that's the piece I did there. For the second version, I really slimmed it down. I was like, you know what? One of the issues that I had by doing the riser was that by putting the original lid back on, it's like it's going way up. And I was like, okay, well, I could just put a cap on top and now I don't have to worry about it. Because part of me was thinking, okay, well, this would actually also help solve the problem of people who sit there and say, when the spools are light, they rock forward, and having this plate right here in the front of the spool would actually stop it from rocking forward, because it would just go bonk and it would stop. Not just from bonking on the top here. I haven't had that problem per se. I've seen the spool where it starts going through and it gets a little light and it comes up, but it has never stopped feeding, never had a problem. It goes till it finishes the spool. It's fine. I haven't had that problem. So some people have weighted their spools. Maybe it's because I'm using the Sunloos, and the Sunloos are very close in size to the Bambus. So they're right there in here. Maybe that's because people were using spools that were shorter and just created more space. I don't know. But I was originally trying to deal with that issue as well when I did that. With this, I just said, you know what? No, we're going to go ultra super simple. That thing took me about a week of learning on shape. Okay? Well, took me about 5-6 days to come up with the window vent system. Took me another week to build that out, and then it took me about 2 days to do this one. So picking up Onshape is really cool. I actually left a feedback for Onshape and the CAD people on their maneuvering system, because I have a huge beef on how they do maneuvering and grabbing objects and swinging around in that world. And it's like, are you guys absolutely stupid? Everybody in the world knows how to do it. It's called flying in 3D. Have you ever seen all the stuff that people make in Minecraft? Not one of the 3D graphic software out there can compete with Minecraft. And Minecraft kicks their ass every day of the week. They've got 166 million users. Why? Because moving around in that 3D space is intuitively easy. Moving around in 3D space in Onshape, 360, SketchUp, I don't care who it is, none of that is intuitive, okay? And it is back-asswards. It is seriously screwed up, okay? And I know why they have that available. I know why their maneuvering system is the way it is, and it is needed, but it is just an absolute crime against nature to me that they didn't include the new standard internet standard, because kids learn that and then they go try to do the new thing, and it's like, it's the same complaint of like parents trying to sit there and go, I'm not going to go learn new math. Screw you. It's like, dude, we all know this. Why do I have to learn something new? You're going against what I do in games every day. And yes, getting people into 3D design and doing this stuff, which is a huge important thing when you look at all of the manufacturing world. Not having it as an additional means of maneuvering is just stupid. That's stupid. I can appreciate you've got the other means. Add this. Make it a secondary method of doing it. There's no reason why you can't. You should have done it a million years ago. And the first company that does it, I don't care if it's AutoCAD or Onshape or whoever, they will dominate the market. Okay? I'm going to give you another example here that I told them. Okay? Back in the 90s, everybody who had a personal computer and was getting one had access to a regular printer, a black and white printer. And they were cheap. You could get them for $200-300. The really cool people had a color printer. Ooh, we had a color printer. But everybody had access to those things. Nowadays, you can get a single color bed slinger from Bambu for like $200. Okay? It's an out of the box, open it up, and it works. How many people love those stupid dragons and buy them on Amazon? Okay? They love to do it. Everybody, how many people today use Photoshop? Okay? Back in the old day, we used to pay for ringtones. Pay for this, pay for that. Now we're paying for this. People, the average person wants Photoshop so that they can edit their stupid, Instagram photos. Everybody wants that stuff. Oh, but nobody has Photoshop. It's all embedded into the phone. Yes, but the phone company didn't invent their own software. They bought from someone like Photoshop who took that software and made it available for the phone. That's where that money's getting made. If you're doing that stuff and making it easy and bring it to consumers, make it easy for them. How do you make 3D consumers easy for them? Use regular fly-in. You make it easy for them and everybody would have a 3D printer. And the cool people would have a color AMS type, whatever type thing. A color 3D printer. Yeah. All right. We would be in that age, but the entire 3D people, they're fighting against it. They're like, nope, we don't want them in here. Because every time somebody comes over, they're like, you have a huge shot at getting somebody who's all excited, and they go, I can't do this. Because having an object stationary in space and getting flung around it is counterintuitive to having a stationary object and you flying around that object. It's crazy. Anyway, so this unit here, it works. I've gone from 64, I'm now down to 27, 24 next to the desk that's in here. Again, you have to have a means of taking increased, your air temperature's been brought up. So now you have a humidity deficit. So it comes in, it says, I'm hot, give me more water. Takes that water, and then it needs to leave. It's going to leave, it's going to get the hell out of there, and then out here, it can drop the water wherever it wants. I don't care. It can cool down and condensate, do whatever, shift into the air, whatever, don't care. Okay? Now the other piece is it is built with hinges that go right in with the existing AMS hinges. So it swings up as usual. You're not really going to need this plate. At least I don't think so. If you get this one, you're not going to need the plate. I keep mine wide open. In case you're wondering what I'm looking at, it's right in here. There is a little plate next to the vent holes right there that, let's see if I can operate this for you. Here, and I've got mine in there nice and tight so it doesn't really move for me, but this slides back and forth so you can adjust how open it is across those vent holes, and so the air comes out right here. If I put my hand, I've got some air hole. Yes, there's a little bit of gap right here just because when I screwed these together, okay, I just used a quick screw together type system. The really awesome desiccant method they have for the AMS Mini or AMS Lite, where they have the little joined piece here. Those are pretty cool. I like that, and I probably will do something like that in a newer version of this. But I'm going to get this version out just so that people have it, because it's kind of really needed for this time of year. And yes, this is kind of, there's been some small adjustments to it, such as the size here so that this fits better. Comes down over here and fits better, fits flush. There's been some small adjustments that I did that I didn't do to my existing working prototype to adjust, so it should fit better and all the rest of that. Again, using this, power comes into basically a central little pigtail. It goes to here, or power in comes here. And if I turn it off, power comes out of the switch to basically a little block. It's it's one of those little, God damn it, it's basically a wire nut, if you would. Anyway, all of the other wires, everything else that needs power is plugged into that. The neutral comes in and it's plugged to all the neutrals and whatever's controlling that neutral. So the neutral goes to the thing here. A power line comes into the relay. Neutral goes over to the probe, and the relay turns on, does all that good stuff. So this is working. One thing you will notice, and it'll be off-putting when you have this heater, and I'm thinking maybe I'll do something about this or try something different, is that you're getting a lot of back pressure. Back pressure is caused when you have a fan that's blowing against something. It can't push the air forward as fast as it wants to. If you have a leaf blower, try this. Take your leaf blower, hold it up in front of you, and take your hand and slowly move your hand towards its opening. At one point, real close to the opening, probably about that far, when you get close to the opening, it's going to sit there and the motor's going to go real loud, and the air pressure, the pressure coming back is going to drop to nothing. Okay? There's a threshold in back pressure, okay, that causes it to just completely force backwards. Okay? And so right now in here, I have a lot more air coming out than comes out on this side. It's actually very slow moving air going through this entire thing. I was looking at trying to do some tests on the airflow control, see if it's flowing around. This is big enough to where you don't really have to do that. Okay? The air is pressed right to the center of the holes. You could say, well, it's going into the center and it's going all the way over to here and then coming out the vent. Yeah, but it's also coming out these little spots right here. And so it's kind of meshing around, and these vents are kind of off to the side, you know, and you've got the airflow, it gets there. It gets there. It's heating up all the air, and it is mixing and circulating. Think of it like a blender. If you turn the blender on and you've got it real full, sometimes it gets that one spot that just doesn't want to mix, right? You've got that one spot, it's not mixing. It mixed at first, and then it's not mixing. And then slowly, over time, it does mix. And if you're leaving this on for hours, if you left the blender on for hours, it would eventually mix and get out. And that's all you got to worry about. All right? It's not that critical thing. If you are huge on time consumption of making sure you get rid of water, okay, well, then go use a smaller one, because that's what you're going to need. For a futuristic, yes, I'm going absolutely overkill on the ability to do this. I'm going to add the third method, which would be the cooling system. And what I'm thinking about doing is basically taking a dehumidifier, running the air through the dehumidifier first to remove water from the air, then bringing it into the heater to increase even higher, to increase its ability to go up. So let's say this temperature allows you to have 75% humidity. If I'm coming in at 65, I'm not creating that much of a deficit. But if I run it through a dehumidifier and I decrease the humidity in that air that's going in here to say 40%, ooh, now I've created an even bigger deficit of 40 to 75. Watch these fans. This fan is fast and it is painful. I actually had it nick my finger right there. It broke skin. Ugh. So, this is it. I'm going to be posting this on Maker World or whatever it is, the Bambu thing. I'll probably put it on printables as well. But as a heated AMS system, it works. Oh, yes, I have a humidity graph right here, but I also have another small one. It does use the little hex ones. You get them for like 2 dozen for $10. They're cheap. I've got a ton of these things. So I've got one inside the desiccant right there. It's reading at about 24 because it's right next to the desiccant. This is reading 28. If you looked a little while ago, it was at least at 30. And outside it was 65. So I am very happy with the idea that it's coming down. This is coming down slowly because it's actually drying the spools that are in here, because I kept opening it up and that moisture gets sucked into the spools. So was having a lot of hard time printing because of the humidity that kind of kicked me. I kind of got this done in time, and then second version, bad timing to have to do it again. If I had just stuck with the first version, it was working and it did the job. Not as efficient, not as nice looking, not as whatever, but it worked. This, well, looks better. Newer version that I'm looking at doing, I ordered basically some PETG sheets. They're pure clear PETG sheets that you get. It's a 5-pack for $10. Again, I know. And I want to slice a hole about right there and put in on the inside a clear piece so that I can see what the levels are on the spools, to see how empty or full they are. I can see what's there. I can at a glance see what colors I've got, whatever. I did this in transparent, but I keep this room relatively dark, and as you know, with transparent filament, it's not really that transparent unless you go absolutely nuts on heating and slow, and yeah, you're not going to get glass. You're not going to get that. So I might as well do that by ordering a small piece. I can make a window right here and it's good enough. So that'll be in the new version, but for right now I'm going to release this without the window. Worst case scenario, dude, just grab yourself your Dremel, cut, and put the sheet on there with some silicone or screws or whatever. You can do it yourself, but I'm going to release this for now because of the weather, and I think there's probably some other people who really want one of these things. Again, I did this so that I didn't have to make any changes to the actual AMS box. I still have the original lid. Okay, so if I want to put this back to normal, I can go back to normal. That's kind of big with me, is I don't want to damage what's pre-existing. When you spend a bunch of money on something, you don't want to destroy it. And I know I can order a new lid, but it's $35. Come on. All right, so I think at this point I'm just talking to hear myself talk. I hope you guys like it. Hope you enjoy. I will put links to the ones I bought. I'm not saying you should buy these. I'm saying this is the one I bought. We'll see if it lasts or if it's any good or whatever. But it is a 200-watt heater. I bought the Inkbird thermostat. I got some switches. I'll have to look these up. I got those a million years ago. I've had them. But I'll put links to different parts that I used. And then I will put links for the printables and Maker World places where I post this. I got to get the files together and get them uploaded. Tell me what you think.